Question 4. A. Outline how energy of a wave can be converted to electrical energy. Now, the energy of the wave is basically mechanical energy. So you have mechanical energy, and that is converted into electrical energy. And basically what happens with mechanical energy is that you cause some sort of oscillation. So you cause something to move to and fro, maybe an air column to move to and fro, that will turn some sort of dynamo. So that it will turn a dynamo, that's a generator, electric generator, into electrical energy. So this mechanical to and fro, this up and down movement, causes some sort of rotation. Sometimes as it goes through, it passes through, you cause an air column, and you have a rotating sort of blade, almost like a windmill, like this, and this moves around, and that causes a dynamo. It causes basically a coil of wire to turn in a magnetic field, and that produces electrical energy. So it says a wave on the surface of the water is assumed to be a square wave of height 2a as shown. The wave has a wavelength of lambda and a speed v, and has a wavefront of length l. So that's actually this length over here is your L. And then it says show that the gravitational potential energy EP stored in one wavelength of the wave is given by EP is equal to a half a squared lambda g. This over here, this is rho, which is the density, and the length. Now you should know that that's the rho is equal to density from that formula here, if you know your formula. So that's the density formula. So we have got potential energy, so we are going to use our formula EP is equal to mgh. Now we know what h is. H, the height, is 2a. Now we are looking at the crest here. So basically what happens, we're actually looking at the height in terms of our crest, which is halfway. So our height is actually going to equal just a. So our height, we would just have it as a, like that. So let's have a look at the other parts here. This m is the mass. Now when we think of it, our rho, which is our density, is equal to mass over volume. So mass is equal to rho times v, which is our v here, looking at our volume. Now what is the volume of this wave? So we're going to have our volume is going to equal, it will basically be this portion over here, because this is your crest, which is moving to and fro. So your volume is going to be that length over there. It's going to be a half wavelength there. This is a and length. So our volume is going to be a half lambda a l. And therefore our mass is going to equal a half lambda a l rho. So we're now going to put it into this formula over here, and we would get EP, our potential energy, is equal to a half lambda a l rho, and then we're going to get G, and our height is equal to a. So we get that formula here, and obviously we've got an a times a, so we get a half lambda a squared L rho G, which is what we have here. Then it says deduce that the gravitational wave power per unit length of the wavefront is given by. So let me just clear this over here. We have power is equal to work over time. So in in looking at over here, the power is equal to a joule per second. Now, we have got our energy, our work, is actually given by this. So we've got our power is equal to a half a squared lambda g rho L, like that. But we've got this per second here that we've got to look at, and also it also says over here per unit length of the wavefront. So we're going to need to look at that also. But let's have a look firstly at this idea of power. Now we know that our formula that we have, that V is equal to frequency times wavelength. So we got that frequency times wavelength. So my frequency, which is a seconds to the -1 value, it's the number of its number of waves per second, is going to equal velocity over wavelength. So this over here per second value will come from that. So I'm going to multiply this by my v, my velocity of my wave, divided by my wavelength, and it's per, you notice here, per unit length. So I'm going to have to also multiply that by 1 over L. That's my per unit length. So that will cancel like that. And my lambda will cancel there. So I'm going to get a half a squared g rho v. Okay, and that's what we have over here. And we're going to need that formula in the next question. So just keep on going. So it says here, it says the density of seawater, so we are given the density, we're given our rho, is equal to 1.2 times 10 to the 3 kilograms per meter cubed. So it's in the right units. Use the expression in B2 to find the gravitational per meter length available in the wave height of 0.6 meters. So the important word here is this idea of estimate. Now, because when I take that formula that I have, I've got this formula, let me just work over here. I have that my power is equal to 1/2 a squared vg rho. Now I've got what my a squared is, or I've got my a. I'm told that my total height for this was equal to 0. Where does it tell us here? It's 0.6 meters. So my a, my height there is equal to 2a. 2a is equal to 0.6. So a is equal to 0.3. So I'm going to have a half 0.3 squared. Now I don't know anything about my velocity of my wave, but I do know my g, and because this is an estimate I can use 10, and I know my rho is equal to 1.2 times 10 to the 3. But I don't know what v is. Now I need to estimate it. So I need to take a guess at what it is. And so I'm just going to guess it's something like 5 meters per second. That to me would seem like a reasonable. In actual fact, they accepted anything from 0.5 to 10 meters per second. So you needed to guess that. So you had to estimate what you think it would be. And so when I put this in, I put it into my calculator, I'm going to get 0.5 times 0.3 squared times 5 times 10 times 1.2 times 10 to the 3. And I get about 2,700. Now, this value here would be a gravitational power per meter length. So it would be here a watt per meter. That would be your final value. And again, this could be an estimate, so there's quite a range of values that you could get for this value. It says in practice, a water wave is approximately a sinusoidal in cross section. So sinusoidal in cross section. Outline whether a sine wave of the same height as in B transfers greater or smaller amount of power than that derived in B2. So let's just go back to our picture here. Now we've got that. Now a sinusoidal wave would be something like this. So I think you can see here that if we took this over here and we took this wave over here like that, that the volume is going to be smaller. So your volume is going to be smaller, and therefore your mass is going to be smaller. Your mass will be less, and therefore the potential energy, the EP, will be less, and therefore your power, because your power is equal to your EP basically divided by your time value, that's going to be less, and so your power will be less. So that's pretty straightforward. And then it says list 2 advantages of the utilization of wave power rather than photovoltaic cells for the generation of electric power. Now the main one that's useful is that this works day and night. So it's day and night, winter and summer. So for instance, in a place like Norway, they could use this, even though they have in your winter you get no sunlight at all. And also an interesting thing about that, this naturally will produce AC current or AC power, where your photovoltaic cell will always produce DC, and your AC power can directly be fed into your national grid or into your grid, your power grid, electrical grid, because that is what is used to transfer power over long distances.